Well, we probably ought to get started. I was just looking at the schedule. We got chemical equilibrium today, chapter 13. And then next Monday, we'll do a review on that one. Then you have spring break. So you got all the spring break to get ready for the exam on chapter 13. All right, so let's get back down here. Set that aside. And we'll jump into chapter 13. Share the slides and make a slideshow. There we go. Okay, do some fine adjusting here. Okay, chapter 13, chemical equilibrium. I may have mentioned when we were in chapter 12 on kinetics that that the order of introduction of these two subjects was important. Chemical equilibrium should normally come after chemical kinetics, simply because, well, I should say this. Even though historically chemical equilibrium was studied first in quantitative detail, the understanding chemical equilibrium is better accomplished by studying kinetics first. And that should become fairly obvious here in just a few minutes. Now, on the chemical equilibrium can be viewed, it's best viewed actually, as you can look at it two different ways. One is what it appears to be from the outside, what we call the macroscopic world. What appears in a chemical equilibrium is that nothing is changing. In other words, once you reach equilibrium, then the concentration of reactants is stable. The concentration of products is stable. But on the molecular level, there is frantic activity. And that's where chemical kinetics comes in. Because the equilibrium is not just a forward reaction. It's also a reverse reaction, where you have reactants yielding products, and they're the coefficients. But it's not just forward. You also have a reverse reaction. And the reverse reaction is really only significant after sufficient concentrations of the products have built up so that you start to get those return reactions. That's why in kinetics, we found it convenient to study reactions in their initial states at the very beginning, when the amount of products is very low, so that the competing reverse reaction is insignificant, and we can study the reaction in that direction. If you want to study the reverse reaction, then you flip it around and make the products the reactants, and then you can study the kinetics that way. But now in equilibrium, we have to come to terms with the fact that once you've built up significant, and it varies with each reaction, significant amounts of products, then you get a competing reverse reaction. And these each have their K values. Remember, one of the problems that we worked had a K in one direction and a K in the other direction. Now the rates at equilibrium, the rates forward and reverse are equal, but the Ks are not equal. Those are constants that go into the rate law for the forward and reverse reaction. But back to the topic. On the molecular level, there's lots of activity. What's known as a dynamic situation rather than as opposed to a static. If you've had physics, you understand the terms static and dynamic. Static would be something in physics like studying the forces applied to a lever, like a seesaw. Right, nothing's moving really, it's just got balanced forces. That's statics. Dynamics is when there's motion involved. Okay, so this is what it would look like plotted out, concentrations of, for this reaction, nitrogen plus hydrogen yields ammonia. That's the Haber process. And it's the one that Fritz Haber developed to supply his native Germany with explosives. The first step in the process is to take nitrogen from the air and combine it with hydrogen, probably from coal or oil in those days, and produce ammonia. And from ammonia, you can go from there to nitrates and develop explosives. But this was the really tricky part, was making this reaction viable, economically viable. Now, why did they have to do it? Well, they had to do it because the world supply of nitrates was predominantly coming from Chile. And it was hundreds of feet deep of bird guano that had been deposited over the centuries, and it was being mined. And that was the natural source of nitrates. There have since been other sources discovered, but Germany was embargoed. So they had to resort to this procedure to make their ammonia and then make their nitrates. So it was absolutely essential that Haber and those who modified his procedure understand equilibrium and kinetics for that matter. And they went even further than that. Of course, we haven't got there yet, but they studied thermodynamics, which was helpful in perfecting this procedure. But at this point, we're going to focus on equilibrium. And if you put nitrogen gas and hydrogen gas in a closed cylinder and create the correct conditions, such as temperature and pressure, of course, will increase their concentration. So pressure is another issue. You start off with very high concentrations. Well, the only concentration of hydrogen and nitrogen, the green and the blue lines. And as they start to react, they produce ammonia. And then ammonia starts to build up. And as ammonia builds up, a competing reverse reaction occurs. And at some point, equilibrium is established where the forward rate and the reverse rate are equal. Okay, and we study equilibrium in terms of concentration, some expression of reactant and product concentration. Typically, that would be molarity, moles per liter. Even gases can be expressed that way. Of course, gases can also be expressed as partial pressures. Remember John Dalton. The total pressure in that vessel is dependent upon the partial pressures of the gases. And since all reactants and products, they're all gases, I'm pretty sure, yes, then the partial pressures would be a valid expression of their concentration. This is just another way of looking at it. The forward rate, the reverse rate are approaching one another. Forward rate is decreasing because the concentration of reactants is decreasing. And the reverse rate is increasing as we produce products. And at some point, they reach equal rates. Okay, now here's a teaser. A teaser for a concept that we're going to introduce at the very end of this lecture. I'll just say it's Le Chatelier's principle. But this is to get you thinking about what's actually going on. In this case, we've got a reaction where water and carbon monoxide are reacting to produce hydrogen and carbon dioxide. And at some point, we establish equilibrium. So the concentrations of each of these components is fixed macroscopically. So what would happen once you reach equilibrium? What would happen if we increase the concentration of water? We just inject some water gas. So this, obviously, the reaction is going to have to be greater than 100 degrees centigrade, Celsius. I keep using the archaic term. So if you inject water vapor into this reaction mixture, what's going to happen? Well, you've increased the concentration of water, and you've essentially disturbed the equilibrium. Right? So if you've got more water and there's still some carbon monoxide in there, then those two are going to react to produce some more product until an equilibrium is reestablished. What about the other way? If we're at equilibrium and you inject hydrogen gas, just the opposite occurs. Now you've got an increased concentration of hydrogen, you've disturbed the equilibrium. So some of that hydrogen will react with carbon dioxide and produce formally reactants until a new equilibrium is established. Okay, now equilibrium, that's a qualitative description of equilibrium with reference to quantitative issues like reaction rates and laws of kinetics. But there is actually a calculation that can be performed concerning equilibrium, and it's called the law of mass action. And it was proposed from the research done by two Norwegian chemists, Peter Wegg and his brother-in-law, Cato Goldberg, in 1864. They were trying to describe driving forces that were behind various chemical reactions. And most of their reactions that they were studying were in aqueous solution. So their natural tendency was to express concentration in familiar terms, like molarity, moles per liter. They understood by this time, I mean, it was becoming obvious. This was shortly after the Karlsruhe conference. So chemists around in the European theater were starting to understand that the processes that were involved in chemical reactions were not dictated by mass. Now, mass is preserved, that's true. The total mass of reactants and the total mass of products is a constant. It doesn't change. But in order to understand the reaction, they needed to understand numbers of atoms and numbers of molecules. And by this time, many chemists were starting to take those rules. The law actually developed by Avogadro and further developed and championed by Cannizzaro. Many of these chemists were starting to take advantage of that. And they'd already developed a way of expressing the concentration in terms of moles in a volume. And these two chemists came up with what they called chemical dynamics was their expression for kinetics. And chemical statics was their expression for equilibrium. So in the interest of chemical statics, equilibrium, they developed this law of mass action. And it's very simple. And it is derived from the balanced equation. Right? So that's convenient. Whereas, chemical kinetics, the overall reaction could not give you the rate law for that reaction. But the law of mass action can be derived from the balanced equation. And this is what it looks like. If you use that way of expressing it, right, reactants and products with these coefficients, then they found, Wade and Goldberg found that the concentration of products as a product, multiply them together with their coefficients as powers of those concentrations in the numerator. Then in the denominator, you put those terms for the concentrations and coefficients of the reactants. So it's very simple. There are only a couple of rules that we have to be concerned with. These are the chemical species. Square brackets, right? Square brackets have come to be used exclusively for equilibrium concentrations. So we're saying with these square brackets that C is at a given concentration at equilibrium, and that's where it stays. As long as you don't disturb it, you don't change the temperature, you don't add components, then that concentration is constant at equilibrium. Later on, we'll use concentrations that are not at equilibrium. And in those cases, we'll use parentheses instead of square brackets. The A, B, C, D are the coefficients, and now they become the powers of each of their respective components. And K is the equilibrium constant. Now, by convention, K is not given units. We exclude the units for one very practical reason. If you look at these, you know from experience that these balanced equations the coefficients, sky's the limit. You could have any combination of coefficients which become powers of concentrations in this expression. So it can get complicated very quickly, and you can have units of measure here that are just, to say the least, unwieldy. So when you find K's reported in the literature or in reference manuals, they will not be reported with units of measure. They will be referenced to a particular reaction. And once you know that reaction, then you know that you need to take care when you're calculating K. Because if you don't calculate K and you have no units to go by, then that requires extra care to get the right answer. Okay, so these are just some conclusions that we can draw and some manipulations that can be performed. So suppose we have this reaction and we calculate the K to be this expression. Okay. Now, suppose we'd rather study that reaction the other way around. Make C and D the reactants. Okay. Now what would the K expression be? Well, let's say this is, we'll just call that K, and I'll fix that K in just a minute. I want to write the expression first. It's obviously a different K, right? Because now we've got products and reactants in the wrong place. Okay, notice anything strange about this calculation? This is the inverse of that one. This is the inverse.
You going to try and go in? I texted Amy and told her the water's still the road, and so she'll be work Thursday since I won't make.
Okay, so that means that this K is the reciprocal of that K. Like that. So if we want to get this K, we have to take the reciprocal of the other K. It's really very simple, but I wanted there to be no mistake about this relationship. If you have to invert an equation, now, why would you want to invert an equation? Remember Hess's law? When we were studying thermochemistry, and we wanted to determine the delta H for a target reaction, a final reaction, but we didn't have it in the literature, so we took individual reactions and added them together in a certain way so that we get the final reaction. And there were rules governing what happened to the delta H for each one of those, so we could add them together and find the delta H for the final reaction. Well, sometimes you have to invert an equation. And if you have to do that, then this is what you do to the K value. You invert the K. All right. So that's rule number one. Rule number two, let's see. Suppose in this process where you're adding equations, you have to multiply your equation by a factor. You know, maybe you need 2 A's, you only have 1, but you need 2 to end up with the equation at the end that's the desired one. Well, if you multiply this by, let's just take an example. Say 2. You have to multiply that whole equation through by 2. What does that do? That makes this 2A, 2B, 2C, and 2D, right? So now the expression for the K, and this would be a different K, would be 2 times each one of these, correct? So this new K, and you remember in algebra, if each of these multiplied factors has a power that can be reduced by some whole number factor, that whole number factor comes out of that expression. You factor it out. So this now becomes like that. We just factored out that power from that whole expression. So what does that mean? That means that this value, the new value here, is equal to the old value squared. So whenever you multiply a balanced equation by some factor, it doesn't have to be 2, it could be anything. It could be 1/2, or it could be 10, whatever it happens to be. That becomes the power of the old K to give you the new K. All right. Here they call it the new K is that factor as a power of the original K. And just a reminder, we don't write units for the Ks. All right, so as long as the temperature is constant, the K is constant. That's the only thing that affects the K is, well, all other things being equal, right? You haven't done any of these transformations. let's just say you've got that original K. What are you going to do to change that K other than reverse it or multiply it by a factor? The only other thing you can do is change the temperature. If you change the temperature, then that changes, we learned from chapter 12, that changes the reaction rates. Right? So now you've got to reestablish equilibrium at a different reaction rate. So the K does change with temperature. Now there's a fine distinction here between equilibrium which talks about the K value, which is constant, and equilibrium position. Equilibrium constant is not the same as equilibrium position. While this constant is in fact, let's see, let's go back. Let's go back to where we were, like this. There we go. The equilibrium K is a constant, but you can start your reaction at different concentrations up here, can't you? Right? Instead of, say, 1 molar and 1 molar, and then it establishes equilibrium. What if you started 10 molar? 10 molar and 10 molar. It's not going to end up in the same place. It's not going to have the same concentration. That's what we call equilibrium position. So while the K is constant, the position varies depending on where you start. So that's an important distinction. And it's basically a set of equilibrium concentrations. And we'll have some examples coming up next soon that will illustrate that point. Now, K, right? K is a constant. It can be anything. Well, in this case, other than potassium. But we have subscripts for K that are specially designed to give us a little more information about what that K references. If we just say KEQ, case of EQ, we're just talking about a general equilibrium constant, which is usually expressed in terms of molarity. In other words, the concentrations are molar when the K, when the K is calculated. The case of W is this very special situation which discusses the equilibrium of water dissociation. So we know that water can do this. Well, maybe you don't know yet because we haven't talked about acids and bases, but we will. But I'll just say that water can do this and it can dissociate, right? Like that. You just break off a proton. Now, it doesn't do that very much. Very few of these over here. Most of it's over here. But there's enough of this to warrant the calculation of an equilibrium constant for that reaction. And the K that we give it has a subscript of W. And when you say KW, it means only that, nothing else. We can also do this for acids. Right, so if you have an acid, then it can dissociate into those parts. Right, and we'll talk about that more when we get to acids and bases. But that we know how to name acids, so we know that they have to be preceded by at least one hydrogen, sometimes 2 or 3. But just one dissociation like that, remove one hydrogen, and you can calculate a case of A for that reaction. Another one. Let's say we have a solid. and we put it in aqueous solution, and it dissociates into those two ions. Right? We can write a KSP, solubility product, for that reaction. Now we call it a solubility product because that's what it is. And that refers to, I'm sort of jumping ahead here, but stream of consciousness dictates that I explain that when we write equilibrium expressions, there are some terms that are not included. And solids is one of them. When you write the expression, you don't include concentration of solid, right? Because a solid has no concentration other than maybe density or something like that. But as the reaction proceeds, the concentration of the solid does not change. It may lose some of it or it may add some to it, but the concentration does not change. So we don't include solids in the expression. Pure liquids, we don't include those either. So when we write this one, liquid water dissociating into these two ions, that expression does not include water because the concentration of water effectively does not change in the process. And that's true for any liquid, any pure liquid. If it's got an L back here or an S, you don't include it in the expression. The only ones for our purposes that we include in equilibrium expression are two, either aqueous or gas, one or the other. Now, if you're actually a chemist and you're researching different non-aqueous reactions, then you would have opportunity to use a different concentration because your solvent would be different, wouldn't be water. But the fact of the matter is solids and liquids are excluded no matter what the solvent is. Okay, so there's one other one that's common. Actually, there are two other ones. And that's case of F. That's the equilibrium constant for formation, the formation constant. These are for complex species. And these complex species are typically soluble. In other words, they form stable compounds. Yeah, you can call them compounds. But they don't precipitate and they don't volatilize. They just stay in solution and affect the reaction. So here's an example that you're going to study later on toward the end of the semester, in the labs, that is. So if we take silver in aqueous solution and we combine it with two ammonias in aqueous solution, then it will form a complex ion. Like that, in aqueous solution. Okay? And you can write an equilibrium expression for that. Here's your product. There's your reactant. There's a reactant. You just write it just like Wade and Goldberg did. There's no difference. And it will produce, it would generate a K value, case of F. And the last one has to do with gases. So if you have a reaction where the only terms that go into the K value are gaseous, it's not a combination of, well, I suppose you could do a combination. Let's keep it pure for now. Nothing but gases. Then you would have a case of P. And then that case of P, say all of these were gases, all four of them. Then you would write this. You would say partial pressure of C to the C power times partial pressure of D to the D power divided by the partial pressure of A to the A power times the partial pressure of B to the little b power. Okay, so you could express those, and typically we write those as atmospheres, at least for this class. We'll keep it simple. And this expression will be different from the K. If you express those terms, those gases, as molarity, you get a different K value. If you express them as atmospheres, partial pressures of each one in atmospheres, you get a different K value. Now they're related, and I'm going to show you how to transition back and forth, but that's just a teaser to let you know that it's coming. So in this case, actually this is a bad choice. When you put parentheses around these, it implies that it's not equilibrium. So we should get rid of the parentheses and just use the partial pressure. Right, for this reaction, you would write it as partial pressure squared for ammonia, nitrogen partial pressure, the first power, and partial pressure of hydrogen to the third power in the denominator. Now, if we express those in molarity, we get a different expression here, and we get a different value. The values are related. Right? So if we calculate the equilibrium pressure, these equilibrium pressures for these gases, right? This would be the equilibrium position under these specific beginning concentration values. Now, these are the equilibrium values. This is the equilibrium position under those conditions. And then we write the expression here, substitute the values for each one. Don't forget your powers, right? Even I make that mistake. Don't forget to apply those powers in your calculation, or you just be completely wrong. Then we come up with this value, 3.9 times 10 to the fourth. And there's that's another reason for putting the P in here, because it means that this K was calculated with partial pressures. Okay, so the relationship between the two, as you may have guessed, involves universal gas constant. Fancy that. And since we're using atmospheres to calculate this, then R is in terms of atmospheres, liter atmospheres per mole K, not the other one with the energy units. All right, and then we need to know the temperature also. Right, what is the temperature? Because the influence of temperature, well, actually, is very simple. We have to factor out the temperature from this R value. Right, so we need kelvins in here to cancel the kelvins in the constant, the R value. That leaves liter atmospheres. And then we need to get rid of liters somehow. Oh, that's in K. K cancels that one out. Okay, now what does delta N mean? Delta N is an expression of the change in the number of moles of gases from the reactant side to the product side. So if you say, oh, well, we're going to use this as an example. So let me go to the next slide. I think that's where it's at. Yeah, we're going to use that same Haber, and we notice that the total moles of reactants is 1 for nitrogen and 3 for hydrogen, which is 4, right? Total 4 moles of gas, and we end up with 2 moles of gas on the product side. So you take the change is like we did with temperatures, final minus initial. So the product moles minus the reactant moles is the value that's delta N. So 2 minus 4 is a minus 2. N can be a minus 2. That means the number of moles decreased by 2. So that becomes your multiplier here on this term, right there. This is your case of P that we calculated earlier, and then we determine K in terms of molarity, moles per liter. Yeah, actually we don't have to cancel liters. It's part of the expression. K is in molarity. Right, so see the values are different because we used different units of measure to calculate each one. Okay, so we can discuss in general terms equilibria as either homogeneous or heterogeneous, and it's really simple. It's like catalysts, you know, homogeneous, everything's in the same phase. Heterogeneous, you have at least 2 different phases. Catalyst is in a different phase from the reactants. Similarly, for equilibrium, homogeneous equilibrium is a reaction in which all of the components are the same phase. All aqueous, all gas. And if you have solids and liquids in there, they don't count. Actually, they do. Sorry about that. That's homogeneous. If you have any solid or liquid in there, or you have a difference from if you have gas and aqueous, that would also be heterogeneous. But this term is not expressed in the equilibrium. This term is not expressed in the equilibrium. In this case, we're taking water and we're splitting it apart. You know, maybe an electric current, a direct current flowing through there, like that example we showed you in one of the slides. The 9-volt battery dropped into slightly acidic water. You just put a drop of lemon juice in there, and that'd be enough to conduct electricity. So that's a heterogeneous equilibrium. Either one of these is an example. Okay. And this is just an expression that probably should have come earlier. When you have pure liquids or solids, the equilibrium expression does not include them. So this solid and that solid go out. The only part of the equilibrium expression that's important, or that we use to calculate, is in this case, the gas, O2, to the 3rd power. That's it. Now that doesn't mean we can't do some stoichiometry, right? Once we determine how much of this, say we started off with just this and let it decompose, right? In the beginning, you had no oxygen. But at equilibrium, we've actually lost some of this and produced some of that, right? So with our equilibrium expression, we can calculate how much of this was produced, and then we can say how much of this was lost. Right? The stoichiometry is still valid above and beyond the equilibrium expression. Okay, something else qualitatively we can assess from the value of K for any given reaction. If the K is much, much larger than 1, and I say that because if it's close to 1, then the powers, these things, they get in the way and they sort of muddy the water. But if the K is very large, like 2nd, 3rd, 4th power of 10, which we call orders of magnitude, then we know that the equilibrium position lies far to the right, right? Because that means the numerator is large, the denominator is small, so the K would be greater than 1, much greater than 1. Consequently, also, if the K is much less than 1, then we know that the reactants are favored, right? Because these are large and those are small. So if it's much less than 1, like 10 to the minus 2, 10 to the minus 3, 10 to the minus 5, 10 to the minus 10, we know that the equilibrium position tends to be toward reactants. And if that K value is small enough, we know that the reaction as written essentially does not occur, not to any significant extent. Okay, just a rehash. Now, I mentioned earlier the use of square brackets for the equilibrium position. If we calculate this value with non-equilibrium concentrations, then we're not calculating K. We give it a new letter. We call it a Q. Right? So if we calculate for this reaction, we calculate Q as equal to that and that divided by that and that. Now, what's the value of doing that? Well, when we start doing equilibrium calculations to actually determine quantitative values for our equilibrium position concentration, we need to know which way the reaction is going to go. If we put some A, B, and some C, D in there, how do you know whether it's going to favor going this way or that way? Well, we calculate the Q. We use the concentrations at the start, and we compare the Q value to the K value. Okay, so the simplest situation is, and the rarest, is when you set up your reaction, if the Q is equal to the K, you're at equilibrium with the concentrations you have chosen. Right? That's the easiest one. Now, what if Q is larger than K? What does that mean? If Q is larger than K, that means we have increased this amount and decreased that amount. Right? In order to make Q bigger than K, this has to be greater than that, and this has to be smaller than that. So that means we're favoring products in our initial concentration. So that means with Q greater than K, we have more of this than we need. So the reaction is going to proceed to the left, as written. Right? And that's important. When you write an equilibrium expression or even a Q expression, it applies to a reaction that is written and balanced in one direction, right, with reactants and products as written. So if you say the reaction moves to the right or moves to the left, if you don't show the reaction that you're applying those directions to, left and right mean nothing. Right? It could be the other way around for all I know. And that's an important point to keep in mind when you complete your lab reports. Unless the reaction is given to you in the question. If the reaction is given to you in the question, then you can go ahead and say left and right, and I know which reaction it's based upon. But if you're describing left and right for a reaction that you have not defined yet, then left and right mean nothing. So if Q is greater than K, we're headed back toward reactants. So obviously, if Q is less than K, we're headed toward products. Because we have, if Q is less than K, that means we have too much denominator and too little numerator. So it's going to go to the right as written. Okay, now we need to say, all right, now that we know that, well, there's also a special case, which we ran into studying chemical kinetics. If you start the reaction with reactants and no products, right, it can only go one way. It heads toward products automatically, right? So in that case, you don't need to calculate Q. It's only if you're at a non-equilibrium position with both reactants and products. Then you have to calculate Q to determine which way it's going. Also, you know, there are other situations that just occurred to me. You don't have to be absent all products to know the direction of the reaction, right? If you've only got D over here and not C, and you have A and B, then it's got to go to the right because D can't go backwards. There's nothing for it to react with. So you know in that case that it'll also go to the right. So in a balanced equation, if you're missing any one of the products, it's going to the right. If you've got all the products and you're missing a reactant, then you know it's going to this, toward the reactants. All right, so here's a sample, an example reaction. We need to make some room. Straighten out my board. I know I moved it. There we go. Here's a reaction where we react iron 3+ ion, probably iron 3 nitrate would be a good choice, or iron 3 chloride would go into solution. And then thiocyanate ion, that's one of those polyatomics that you had to, well, you didn't have to memorize, but hopefully you studied in that chart from last semester, actually. And we put them together in solution and they react to form this complex ion. Right? So what does that look like? It looks like the example I showed you with silver and ammonia. Right? You form a complex ion with this one and that one, it forms this one. Right? And the reason we use this is because iron in solution is going to be sort of yellowish. Thiocyanate's colorless. When you put them together, they turn brick red. So it's easy to observe the change as the reaction proceeds. But we want to be quantitative also. So we have this reaction. And I'm going to leave out the aqueous. Everything's in aqueous solution. And that'd be 2+. Charges have to balance. So what would be the equilibrium expression for this equation? Right? You just take that one. It's nice of them, right? There are no coefficients. Well, actually, there are coefficients. 1, 1, and 1. So the K, and this is a formation, K of formation, like that. So we put this value on top. Actually, hold a second. There, to the first power. And these two on the bottom. Each to the first power. There we go. Now, we're given this information. 6 molar iron 3+ and 10 molar thiocyanate are mixed at a certain temperature, and at equilibrium, the concentration of iron thiocyanate is 4 molar. Okay. What's the equilibrium constant? All right, I'm going to show you a method. It's called ICE. We set up a table And I like to set up the table so that the components or the columns of the table are situated under the balanced equation. So we have this one. So what does that stand for? I stands for initial. C stands for change. And E stands for equilibrium. Okay, what are the initial conditions for this one, and that one? Well, it says we start off with 6 molar, right? 6 molar of this. And we start off with 10 molar of thiocyanate. Right? How much of that do you have when you start? 0. So we know which way the reaction's going, that way. But we also know the equilibrium concentration of that right there, which is 4 molar. Okay? We know it's 4 molar, so how did it get there? Well, we had to add it here. That's the only way you can get a total of 4 molar is to add it to 0, 4 molar. All right, so if that's 4 molar, where did it come from? Well, you had to lose 1 to 1 to 1. So that means if this is plus 4 molar, this has to be minus 4 molar. And this has to be minus 4 molar. Okay? Now, what's the equilibrium value for each of these? Well, 4 from 10 is 6. And 4 from 6 is 2. All right, now you've got your equilibrium concentrations. And you can calculate this value. Right? So this value is going to be 4. And this value is going to be 2. And this value is going to be 6. Which is what? Well, 4 divided by 12 is like 1/3. Right? Divide 4 into the whole thing. Right? 4 divided by 12, same as 1 divided by 3. There's your K value. All right, now what can you do with it? Once you find out what the K value is, what can you do? Well, it's like any equation. If you know the K value, and you know either one of these, then you can solve for the third one. Or, if one of these happens to be unknown, then you can just play algebra and say the unknown is X. All right, and we're going to do that in just a minute. So now that we have K, and this is what it's on this slide for you. I just thought it might make more sense if I went through it like this first, rather than just throwing it up on the board, throwing it up on a slide. I threw it up on the board here. So K is 1/3. Now, if we have an initial concentration of iron here, and we have a different concentration, I actually have 2 different concentrations. So we have a K value, and we're not changing the temperature. The K value is constant, but we're starting at a different place here and here. So that means the position, the equilibrium position, will be different. All right, so let's do that. We've got 0.33. Let's put that over here. We calculated that already. All right. So let's remove that because we're going to have to put something else in there. Now we've got iron, thiocyanate, and the complex ion, but we've got different starting positions. So let's erase this stuff. And you should become proficient using ice tables because you're going to see them again, not just in this chapter. When we get to acids and bases, we're going to use them extensively. Okay, so our starting position is 10 molar iron. I'm going to leave out the molar part, just to understand that that's molar. And then we have 8 molar here, and we have 0 here. Okay? Now, what's the question? We want to know the final concentration of this ion, right? So here's where it's important that you choose your unknown wisely. If you choose your unknown such that the X value, the unknown value, is equal to the answer that you're looking for, that simplifies the whole situation. Sometimes you can't do that, but when you can, do it. We want to know what this is right here, right? So why don't we make that X? Okay, that's our unknown. So how did it get there? Well, we had to add it here, didn't we? Just like before, when we had a real number, now we got this unknown. We had to add that much to make this. So where did that come from? Well, it's 1 to 1 to 1. So we had to lose an X here and lose an X there in concentration. So now our equilibrium position is 10 minus X for iron and 8 minus X for thiocyanate. Now we have an equation where we know that one, and we put values in here for this one and this one, this one, this one, and this one. And there's still one unknown in there, the X. And the X is what we're looking for. Right? So we would fill in the table like this, with that value, this value here on top. Right? Well, let's be consistent. There you go. And this one for iron, I'm going to drop some of these zeros off here just for convenience. There you go. So that's our expression. This is equal to that value. So you can solve for X. Only it can become sticky, right? Especially when you have lots of powers in here, because you can get some pretty huge polynomials. Remember that from algebra? A polynomial has several factors where X is powers. To the second, to the third, to the fourth, to the fifth power, polynomial. So when you get that high in powers of X, then there may be formula that have been developed, but they're extremely complex. And you only want to use them if you have a computer at your beck and call. So really the only one that we would be interested in using is if we had a quadratic equation. If we had x squared, something times x, let's say ax squared plus bx plus c equals 0. That's our quadratic. And I've got the formula on the back of my calculator, so I don't have to remember it. That's one possibility. If you have a bona fide quadratic equation. Sometimes you can simplify it, right? Where does the x squared term come from? Down here, right? So if you can get rid of one or both of those x's and leave this one alone, then you've got one x to solve for, right? Or even if this one is squared, if you can get rid of those, then you can simplify it to where you only need to take the square root of both sides. That's another possibility. But if you're forced to use the quadratic, then go ahead and do it. And I'll tell you under the conditions, I'll tell you when you can use that simplification. Let's see, where was I going with that? Oh, there's also one other way to do it, and that's the way that many chemists use. It's called the method of successive approximations. So even if it's not valid for you to eliminate these x's to simplify the calculation, go ahead and do it. You get a value for x. Then the next time around, you plug that x in here and solve for x again. And you get closer to the answer. And sometimes you may have to do it a third time. Substitute the new x for here and solve for that x. Then you approximate and you get closer and closer and closer. How do you know you're getting closer? Well, we're going to calculate that in a few minutes, called the 5% rule. If you get within 5% of the expected value of k by using the x that you determined, then you're good. So let's calculate this. Let's do it quadratically first. Okay, so we've used our ice table. Now we need to resolve that formula. Now I might have to make some room here. Okay. So this is going to be 0.333, and we have actually, these two terms can come over here. And then x stays on that side, like that. So I took these two, put them over here, like that. Now we need to resolve these terms. Okay? So how do you expand a quadratic? Okay? You take 10 times 8, then you take x times x, or minus x times minus x, and then you take 8 times x plus 10 times x. That's how you expand a quadratic. So this term would be, let's see. I want to be sure I wrote that correctly. Yeah, okay. So this would be 10 times 8 is 80. And then this term would be x squared, right? A negative x and a negative x, x squared. And then 8 times x is a minus 8x, and a minus 10x is a minus 18x. Like that. Then this whole thing is multiplied by 0.333. So I'm going to expand this over here and then put it equal to x. So what's 0.333 times 80? I have to use my calculator. $2.664. Right? Then minus 18 times 0.333. 5.994 x. Then plus 0.333 x squared, and that's equal to x. So now, remember, quadratic equations can't be solved with that formula unless everything's on one side and zero's left on the other side. So we need 0 over here. That means subtract x from both sides. So that means it comes over here as a minus 1x, which means minus 6.994x plus 0.333x squared equals 0. And this is 2.664. Okay? Now, we have to resolve this with a quadratic equation. Right? So you need to remember the structure of a quadratic. I've flipped it backwards. This is the a term. Ax squared plus bx plus c. So when you write the quadratic, I'm going to have to erase some of this. So when you write the quadratic, your solution then is equal to, see, I can't even remember. Ax squared. Wait a minute. No. That's stupid. Minus b plus or minus the square root of b squared minus 4ac divided by 2a. So these a values come from here. B values come from here. C values come from here. And notice that we've got a plus and a minus. So the quadratic gives you two possible answers. In mathematics, both are valid. But in chemistry, only one can be valid. And I'll show you the example. So let's go over here. Let's see. Here we go. So let's see. Did I get all my right terms? There. Oh, I messed up. Here. It's 26.64. Okay, so if we plug them into the quadratic equation, this is what it looks like. Right? Then if you solve it for the plus term here, and then solve it for the minus term, you get this versus that. And then you have to decide, well, which one makes sense, right? If x is close to 16, how did it get there? Well, they're 1-to-1-to-1 relationship, right? One coefficient, one coefficient, one coefficient. So if there's 16 on this side, there had to be at least 16 on this side, and there's not. So that's why 15.99 is invalid. So you choose the other one, right? 5, x is 5. 5 molar. Now, what's left over? Well, you have 5 molar of the thiocyanate, iron thiocyanate complex. Then the thiocyanate that's left over, right, is 1-to-1-to-1. So it has 3 molar left over. And this one has 5 molar left over of iron. That's the new equilibrium position. Remember from a previous slide here, equilibrium position is 2, 6, and 4. Right? That's a lot different than 5, 3, and 5. But the K is still the same. It's just a different equilibrium position. All right. So if we go through that same process again, but we have a different starting point, then we end up with a different value. Right? 3 now. If we start from 6 and 6, we end up with 3 molar iron thiocyanate. And that leaves 3 of these behind and 3 of those behind. So it's 3, 3, and 3 in this case. Okay, when you solve equilibrium problems, you have to, actually, even before you write the balanced equation, you have to be sure that your compounds are written correctly. But that's implied in the balanced equation. So if you don't write the compounds correctly, the equation will not balance. And you'll figure that out pretty quick. So you write the balanced equation for the reaction because you're going to need the coefficients. Then you write the law of mass action for that equation. Then you set up your ice table. You list the initial concentrations. If necessary, you calculate the Q to know which way the reaction proceeds, right? Because in this case, well, I've erased it now, but in this case, we had plus X over here and minus X and minus X. But if we went the other direction, then you'd have a minus X over here and a plus X and a plus X over here. And that would change the calculation considerably. So if you need to calculate the Q, that is, if you have initial concentrations of each one of these, then you have to calculate the Q to determine what's the direction of the reaction. All right. Then this is a statement, number 5, on choosing your X wisely. We chose X in this previous example so that X, when we calculated X, that would be the answer. Then once you've determined what the equilibrium concentrations are, even with their unknowns incorporated, like the X's, then you plug those into the equilibrium expression and solve it. And then you might have to use the quadratic, or if you've got a cubic or a 4th power, or 5th power, or 6th power equation to work with, then you have to use approximations. So here are some examples. I'm not going to beat you to death with these. The answers are given here, and you can verify those yourself. Just use exactly the same procedure that we did up there. And these are probably solved with the quadratics. What I'd like to do, if we have time, is perform this calculation using successive approximations, because we know the value of X is 5. X is 5 under these conditions. So 5 is a significant fraction of 8, significant fraction of 10. So we cannot ignore it. Sometimes you can. If it's very, very, very small, then you can let that X go. But that depends on the equilibrium constant. If the equilibrium constant is a very, very small number, that means there's going to be very little X over here. Then you can ignore X. And of course, we calculate the percent difference to determine if it violates the 5% rule. But if we were to do this by successive approximations, that would be we probably ought to do that. So we did it quadratically. Let's do it by approximations and see how many times it takes to get close to 5. There we go. Okay. All right. So let's suppose 0.333 equals this value. Actually, let's say approximately X divided by 10 times 8. That's where we ignore X for our first iteration. So now this will be 80 times 0.333, right? 26.64, that's where I made my mistake earlier. 26.64 is equal to X. That's a long way from 5. Okay. So now what do? Well, we plug that X into here, which is really going to mess things up, but we'll try it anyway. So now we have 0.333 is approximately equal to X over 10 minus 26.64 times 8 minus 26.64. So what would that be? Well, this is going to be a negative, and that's a negative, so we're okay on the signs. It'll be a positive number. So let's say 10 minus that one is minus 1664. And then 8 would be minus 18.64. Okay, so let's multiply those two together. And I'm going to have to put one of them in manually. 310.2. So that's, then X would be 0.333 times 310.12. I think this one's going to be even worse. Yeah, 103. So we're going the wrong direction, aren't we? So successive approximations doesn't work here. My guess is we would have to put the X in here and leave these alone, which makes for a quadratic, and that okay, bad example. I never tried that before, so I learned something new. It doesn't always work. My guess is that what you would want to do is start someplace, right? So you could start with maybe 4 or a 5 there, right? If you start with a 5, of course, you're going to get the right answer right away, just by chance. But you would have to start with something that's reasonably in these range, right? Because when we say X is 26.64, it can't be. It's impossible. Right? Because for the same reasons that we choose the quadratic choices, the two answers for the quadratic, 26 can't be. So you would have to just pick something. Pick something that's reasonable. You could even pick 8. Say all of that's used up and plug 8 in there. Then see what happens. Then I think you would end up with a valid approximation. All right. That's enough of that. Let's move on. So, is this balanced? No. It's got 2 nitrogens on the product side and 1 nitrogen on the reactant side. So we got to balance it. And then we read the conditions. 2 mole sample of ammonia is introduced into 1 liter container. What's its concentration? 2 moles per liter, right? At a certain temperature. So this is actually going the reverse direction from the Haber. Right? We just flip the equation. So ammonia will dissociate into nitrogen and hydrogen gases. At equilibrium, 1 mole of ammonia remains. So we've used up half of it. Right? We've gone from 2 to 1. So now the concentration is 1 molar. We went from 2 molar to 1 molar. Calculate the value of K. All right, so we need a balanced equation. Oh, it's not going to do it for us. I thought it was going to do the calculation for us. Okay. We can do it ourselves. There's plenty of time. Let's see, let me fix this again. Oops. There we go. All right, so what's our balanced equation? Well, we've got ammonia on this side, and it's dissociating into nitrogen and hydrogen. Right? Those are all gases, so I'm not going to write the G in there. So how would we do that? Well, we need 2 of these over here. Right? That gives us 6 of these. So now we're balanced. So our ice table looks like this. We started with 2 molar concentration of ammonia. And none of that. And then it said, what's the ending condition? 1 mole of ammonia remains. 1 mole per liter, right? So what had to be the change? Well, we had to lose 1 molar. So if we lose one of these, how many of those do we have? Just half as much, right? 0.5. And how much of this? Well, 3 halves as much. Right? So that would be 1.5. Correct? 1 unit is 0.5, and we have 3 of those, 1.5. 1 unit is 0.5, we have 1 of those. There we go. So now our equilibrium concentration is this. What's our expression for K? Well, it's N2 to the first power, hydrogen to the third power, and ammonia to the second power. Okay. So we just plug in the numbers. N2 is 0.5. H2 is 1.50 cubed. And ammonia left over is 1 molar squared. Right. So we just whip out our calculator and say, I'm going to cube that one first. .375 times 0.5, and then divided by 1 squared, 1.69. Rounded off to 2 decimal places. Actually 3. That's our K value, 1.69. Okay, that was a fairly simple one. And the reason it was simple is because we were actually given a final concentration of one of these components. When that happens, it's really easy to figure it out. You just have to go back to the stoichiometry of the balanced equation. All right. Okay, let's see. Do we want to tackle this one? Let's see. We got till noon, don't we? Yeah, we got time. Let's do this one. Let's see, before I go any further, let me be sure I didn't miss some people. Galen, Jackie. No. I don't think Cody ever showed up. Actually, we've lost some people. Okay. So, our balanced equation. Dinitrogen tetroxide gas is in equilibrium with nitrogen dioxide gas. And we know the K. K value is given. We want the equilibrium concentrations of each one of these. Okay? So we have an ice table. We have 1 mole sample of N2O4 is placed in a 10-liter vessel. So we know that this is the only component and it's going that way. So 1 mole in 10 liters is what concentration? 0.1 molar. With none there. Okay, that's it. We're only given that plus the K. So we have to say, what's going to happen? Well, we're going to end up with some over here. But if we have to calculate the concentrations of both, then it'd be nice if to calculate this one if we took an answer and multiply it by 2. So let's make this one the X. So we lose some of that one. How much of this one do we get? We get twice the amount of that one, right? 2 to 1. So now this value is 0.10 minus X, and this one is 2X. Okay? Now we can plug it into the formula. Let's see. What does it look like? K is 4 times 10 to the minus 4 equals concentration of NO2 squared divided by the concentration of N2O4, which is equal to 2X squared over 0.10 minus X. Right? So that term is equal to this term. So if we multiply, let's think about this for a second. Look how small that value is. Is there going to be a lot of this over there? There's not going to be much over here at all. So we can use our approximation and say this is approximately equal to 2X squared divided by 0.10. Right? We can drop that X because we know it's going to be very small. We're going to lose just a little bit of that and get very, very little of that. So now let's solve the equation. If this is equal to 4 times 10 to the minus 4, then 0.1 times that would make this 4X squared, right? Square that term. And then multiply this one times that one, 4.00 times 10 to the minus 5. Maybe we should have chosen something besides X, right? Because when we start getting into exponential notation, we get confused on which one's the unknown and which one's just times 10 to the power. But we're kind of stuck right now. Okay, so this X squared is equal to 4 divided into this one, right? Divide 4 into both sides. So we get 1 times, that's squared, excuse me, times 10 to the minus 5. And then X is the square root of 1 times 10 to the minus 5. So X is equal to 3.16 times 10 to the minus 3. 3.16 times 10 to the minus 3 is X. So what's the concentration of this one? Well, it's 0.1 minus that value, right? So this one is equal to 9.68 times 10 to the minus 2. 9.68 times 10 to the minus 2. And this one is 2 times the X value. (6.32) times 10 to the minus 3. 6.32 times 10 to the minus 3. Okay? So I think we were correct in saying this is going to be so small. Look how much smaller it is than 0.1. Right? It's 2 orders of magnitude smaller. But there's a calculation we can do to verify that we have not violated the sanctity of the unknown. So what you do is you take this expression here and you plug in that x value here and here, and you calculate that and compare it to the accepted k value. Right. So what we would have to do is, I'm going to have to erase this. We would take that x value and put it in this expression. So 2 times 3.16 times 10 to the minus 3 squared divided by 0.10 minus 3.16 times 10 to the minus 3 . You know what? This one is that value right there, squared. And this one is that value right there. So we just square that value. Four times 10 to the minus 5. Divided by this value, which is that one. Right? Look at there. There, there, there. Divide that one into it. And we get 4.1 times 10 to the minus 4. 4.1 times 10 to the minus 4 is our calculated k value with the x included. Right? And our accepted value is 4.0 times 10 to the minus 4. Okay? So how do we apply the 5% rule? How do you calculate percent error? You take the final minus the initial divided by the initial. So we take this one minus that one divided by that one. And let's see what we get. So these are all 10 to the minus 4. I better use the whole thing. So let's say, oh, excuse me, that's wrong. Minus. So this minus will give us a value 10 to the minus 4, and this value is 10 to the minus 4. 10 to the minus 4 is going to cancel. So we just say 4.1 minus 4 is 0.1 divided by 4 times 100. Okay. So, well, let me just do it. I mean, I could do it in my head, but is 2.5%. Okay. So that's less than 5% error. If you wanted to get closer, just take this expression and plug x in here, right there. Plug that value for x here, in here. Then recalculate for x, and you'll get closer, much closer. In fact, it'll probably be less than 1%. But for all intents and purposes, we have our answer. What I was going to do is say, all right, what does it take to make that 100? 25, right? So we say 25 times 25. All right, so that makes this one 100, which cancels that one. And 25 times 0.1 is 2.5. So you can do it in your head if you have experience with that. Okay. So we got that one. Don't need the quadratic anymore. Oh, I need to go down and be sure I got the right answers, right? Right, standard notation and scientific notation together. We're good. Okay. Reestablish my position here with the board. There we go. I got some, okay, this is the last topic for today, Le Chatelier's principle. And I've got some videos that I hope will help explain some of this stuff. But Le Chatelier's principle that I offered as a teaser at the very beginning of this lecture simply says that a system that is at equilibrium, if disturbed in any way, is caused to shift. Now, let's just say disturbed. Such as what? Adding a reactant, adding a product, subtracting a reactant, subtracting a product, changing temperature, changing volume. Anything that disturbs the reaction will be responded by the system as though it's as though it's thinking. You know, it's going to respond in such a way as to minimize or mitigate that disturbance, and it will reduce the change. So reducing the change, for instance, if you add something, it'll react in such a way as to use some of that up. Okay, first scenario, concentration. That's the easy one. In other words, the system will shift away from the added component. Or if the component is removed, it'll shift back to supply some of that component. And that could be either direction. However you write the equation, it could shift one way or the other. You just have to say to yourself, where's the disturbance? And what movement will alleviate that disturbance or minimize that disturbance? So here's your first video.
The Chatelier principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the
Hold on a second.
stress. We will look at a series.
Oops, sorry. I want to maximize the sound. Here we go. Let's try that again.
The Chatelier principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 iron and thiocyanate ion, if we add some iron plus 3 in form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case, the forward direction. Now we'll add 0.1 molar potassium thiocyanate, the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 mole sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the ion. We will now add solid potassium chloride to the solution. We notice the decrease in color, indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is a white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Okay. So there are some examples. In fact, I think your Le Chatelier's lab uses iron and thiocyanate in a couple of the places there. So that's a good introductory so that you know what to expect. Now, that was concentration. What happens when you change the temperature? Remember we said that and we know that the rate law shifts, the K value there changes when we change the temperature. And that change in the rate constants also causes a shift in the equilibrium, which has an impact also on that K value. So the K will change, but it depends. If you're going to change the temperature, it depends on whether the reaction is endothermic or exothermic. So let me explain. If you have reactants in equilibrium with products, if the reaction is endothermic, that means, and this is the way I look at it, that means that the enthalpy of the reaction enters the reaction as a reactant. Right? because endothermic means the heat's going into. So the heat here goes into the reaction and is stored in the products, right? That's why the temperature decreases typically. So with that term as a reactant, what if you add heat? You increase the temperature. If you add heat, you're adding this component, which drives the reaction toward products. Okay, endothermic reaction. Exothermic reaction the reaction is giving up energy as heat, right? So it's stored in the reactants over here, but over here you have products plus released energy that was stored over here. So in that case, this is an exothermic reaction. If you increase the temperature for this one, then you're actually adding heat to the product side, and the reaction shifts toward the reactants. Now that's a convenient way to look at the situation, but what actually happens is in each one of these different types, the endothermic versus the exothermic, you're changing the K value. The K depends upon temperature. But this is a convenient way to look at the reaction so that you can make predictions. So the next video is by a different narrator, so you have to sort of adjust your ear to catch what they're saying and how they're saying it.
This is MSJ Chem. In this video, I'll be looking at Le Chatelier's principle and temperature. Changes in temperature cause a change in the equilibrium position and in the value of the equilibrium constant Kc. Here we have the chemical equation for the Haber process. In the Haber process, nitrogen and hydrogen react together to form ammonia. The forward reaction of the Haber process is exothermic. This can be seen by the negative value for the change in enthalpy. If the forward reaction is exothermic, the reverse reaction is endothermic. We can see this by looking at the sign of the enthalpy change, which is positive. So when we use Le Chatelier's principle to predict in which direction the equilibrium position will shift, we need to know if the forward reaction is endothermic or exothermic. If the forward reaction is exothermic, the reverse reaction is endothermic, and vice versa. Next, we'll predict in which direction the equilibrium position will shift when the temperature is increased. When the temperature is increased, the equilibrium position will shift to the left, which is the reactant side. And the reason for this is that the system will absorb the extra heat, favoring the reverse reaction, because it is endothermic. When the temperature is increased, the reverse reaction will be favored because it absorbs heat. Therefore, the equilibrium position will shift to the left, in the endothermic direction. Next, we'll predict in which direction the equilibrium position will shift when the temperature is decreased. So when the temperature is decreased, the equilibrium position will shift to the right, which is the product side. And the reason for this is that the system will produce heat favoring the forward reaction, because it is exothermic. When the temperature is decreased, the equilibrium position will shift in the exothermic direction, which is to the right. Next, we look at the effect of temperature on the value of the equilibrium constant Kc. So for an exothermic reaction, increasing the temperature shifts the equilibrium position to the left and decreases the value of the Kc. So as we saw in a previous slide, the forward reaction of the Haber process is exothermic. Here we have the equilibrium constant expression for the Haber process. When the equilibrium position shifts to the left, the value of the numerator decreases and the value of the denominator increases. Therefore, the value of the Kc decreases. So an increase in temperature for an exothermic reaction results in a decrease in the value of the Kc. For an endothermic reaction, increasing the temperature shifts the equilibrium position to the right and increases the value of the Kc. here we have the reaction between hydrogen and carbon dioxide to produce water vapor and carbon monoxide. As we can see from the sign of the enthalpy change, the forward reaction is endothermic. And here we have the equilibrium constant expression for the reaction. When the equilibrium position shifts to the right, the value of the numerator increases and the value of the denominator decreases. Therefore, the value of the Kc increases. So for an endothermic reaction, an increase in temperature results in an increase in the value of the Kc. So let's end with a summary, starting first with exothermic reactions. When the temperature is increased, the equilibrium position shifts to the left and the value of the Kc decreases. And when the temperature is decreased, the equilibrium position shifts to the right and the value of the Kc increases. And finally, for endothermic reactions, when the temperature is increased, the equilibrium position shifts to the right and the value of the Kc increases. And when the temperature is decreased, the equilibrium position shifts to the left and the value of the Kc decreases.
Okay. So, about the Haber process. When Fritz Haber first tried to figure this one out, where he combined N2 with H2 to yield NH3, and we need 2 here and 3 here. He noticed that, well, he knew that the reaction was exothermic. So he had 2 problems to overcome. One was, we know from chemical kinetics that there is a minimum activation energy for that reaction. Right? He had to meet or exceed the activation energy to get this reaction to go. That'd be several hundred degrees Celsius. Right? But when he made the temperature higher, he was adding heat and driving the reaction this way, right? So it was defeating the purpose by increasing the temperature to meet the activation energy. He was actually driving the equilibrium to the left. So how did he overcome that? Well, this is increased temperature. So how did he make the reaction proceed fast enough to the right to make it economically viable? He introduced a catalyst, right? So it could increase the temperature to meet the activation energy. But if he introduced a catalyst where the activation energy was actually decreased, then he could actually reduce the temperature from the initial starting point. It's still several hundred degrees. But this way, he was able, in one pass, to increase the efficiency to about 15%, which may not seem like much, but when your efficiency was less than 1% and you got 15% out of it, then that's a major step forward. All right. So that, he had 2 obstacles to overcome: activation energy and equilibrium position. The equilibrium position now is far enough to the right so that they could get some product out of it. So the Haber process in its modified form will produce over 90% efficiency in this reaction. So how did they accomplish that? Well, the boiling point of these 3 gases are different. Right? So if you decrease the temperature far enough, you will liquefy them. I don't know what hydrogen is, but I know nitrogen is -195 degrees C, Hydrogen is probably lower than that, since it's a smaller molecule. And this one is much, much higher than that. So you only have to chill the reaction mixture a little bit, and this will drop out as a liquid. Then you take the gas flow and you run it back through the reactor. Well, minus this, right? So the equilibrium says that if this is missing, it's going to go that way some more. So they keep cycling through the reaction mixture until they get 95+% efficiency, right? It just involves chilling that gas, the product, out. They remove the product and just run the gases back through. And if you, as a chemical engineer, if you feed gas in here, nitrogen and hydrogen gas, in sufficient quantity to make up for the loss of this one, then you can run this process continuously. And this chiller side drops out a liquid that's pure ammonia, and then it goes into a different stream. I mean, either keep it liquefied and ship it off to another factory, or run it to a different process, right? Run it straight into making nitrates and explosives and so forth, or fertilizer. So there's a problem where you have kinetics and equilibrium working at cross purposes, and that's the solution. All right, so we got one more video, I think. Talks about pressure. All right, when you change the pressure of a system, what effect does it have? Well, if there are no gases, right? If they're all liquids and solids, then there's absolutely no effect of pressure, right? Because solids and liquids don't enter into the equilibrium question anyway. But if you do have gas in there, then there's a second question. Does the reaction produce more moles of gas total as a product, or fewer moles of product? If they produce exactly the same number of moles on the product and the reactant side, then changing the pressure has no effect. And I hope this video will explain that.
The pressure of a system can be changed by either adding or removing a reactant or product, or changing the volume of the reaction vessel. The first point has the effect of increasing the concentration of the reactants or products. The second point refers to Boyle's law. Boyle's law states that pressure and volume are inversely proportional at constant temperature. This can be written in equation form as P times V equals constant K. Changes in volume will affect the pressure of the reaction vessel. For example, if the volume of the reaction vessel is increased, the pressure will decrease. And if the volume of the reaction vessel is decreased, pressure will increase. It should be noted that changes in pressure only have an effect on the equilibrium position when there are different amounts of gaseous molecules in the reactants and products. So next we look at some examples. The reaction we look at is the Haber process, in which nitrogen and hydrogen react together to form ammonia. In this equation, we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. This means on the reactant side, we have more gaseous molecules, and on the product side, we have fewer gaseous molecules. When the position of equilibrium shifts to the side with a fewer number of gaseous molecules, this results in a decrease in pressure. And when the position of equilibrium shifts towards the side with a greater number of gaseous molecules, this results in an increase in pressure. So when we make predictions about in which direction the position of equilibrium will shift or changes in pressure, we need to consider the number of gaseous molecules in the reactants and products. So in the next example, we'll predict in which direction the equilibrium position will shift when the pressure is increased. An increase in pressure shifts the equilibrium position to the right, which is the product side. So the equilibrium position will shift to the right because there are fewer gaseous molecules on the product side, which lowers the pressure. As we saw earlier, there are fewer gaseous molecules on the product side of the equation. When the pressure is increased, the equilibrium position shifts to the side with the fewer gaseous molecules, which has the effect of lowering the pressure of the system. Just like the changes in concentration, changes in pressure do not affect the value of the equilibrium constant Kc. In our next example, we will predict in which direction the equilibrium position will shift when the pressure is decreased. When the pressure is decreased, the equilibrium position shifts to the left, which is the reactant side. So the equilibrium position will shift to the left because there are more gaseous molecules on the reactant side, which increases the pressure. Because we have more gaseous molecules on the reactant side, an increase in pressure will shift the equilibrium to the left. And once again, the value of the Kc does not change. In our last example, we look at changes in pressure when there are the same number of gaseous molecules in the reactants and products. So in this reaction, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So the position of equilibrium will not change because there are the same number of gaseous molecules on both sides of the equation. So if we have equal numbers of gaseous molecules in the reactants and products, changes in pressure have no effect on the position of equilibrium. So let's end with a summary. In this table, we have change to the system at equilibrium, change in equilibrium position, and change in the value of the Kc. When the pressure is increased, the equilibrium position shifts to the side with fewer gaseous molecules. When the pressure is decreased, the equilibrium position shifts to the side with more gaseous molecules. And changes in pressure when there's equal numbers of gaseous molecules in the reactants and products has no effect on the equilibrium position. And as we can see, the value of the Kc does not change when changes are made to the pressure of the system.
Okay, let's see. Oh, that was it. Stop the share. Okay, there was one point when I was talking earlier about the changes to the K value when you modify the equation. Right? If you invert the equation, then you derive the new K by taking the inverse. If you reverse direction of the equation. If you multiply the equation by a factor, then that factor becomes the power of the old K to give you the new K. But I didn't say anything about what happens to the K when you add 2 or more equations together. So I thought what I would do was I will take the your review document, and one of the problems in here, number 26, is an application of Hess's law, sort of, but with the twist of determining what's the K value for the new equation. So we're given these 2 equations. Solid copper plus oxygen gas yields 2 copper 1 oxide solid. Okay, and that has a K value that we're calling K1. All right. First of all, what type of reaction is this? You know, just for a refresher. Well, you got copper here as an element, and over here it's in a compound. So remember from first semester, that means it's a redox reaction. But it's a special kind of redox reaction because oxygen is one of the reactants. It's a combustion reaction. So you're combusting copper to produce copper 1 oxide. Okay, so let's go to the second equation. this one, let me give myself some room, because we might have to modify that equation before we can add them together. So let's put this one down here. Copper 2 oxide yields, well, actually it's in equilibrium. Half oxygen gas. K2. All right. So, oh, and we need a target equation. So the target is going to be 2 copper plus oxygen gas yields 2 CuO solid. That's our target. Now, if these equations were perfectly aligned and we could add both of them together and get this reaction, then the K for this reaction would be the product of those two. So when you add equations together, you take the product of the K's. And we could prove that the same way we did the others for the power and the reversal. We can just show you how it works. But we can't just add these two together, because they won't give us this reaction. Right? We need to adjust them so that we have 2 coppers on this side. Right? So we got 4 coppers here, and we need 2, and there's no more copper. There's no more copper down here, so we have to adjust this one to give us only 2 coppers. Right? So if we say 1/2 of this one, we get 2 copper plus 1/2 oxygen and copper 2 oxide solid. So what does that do to the K? Well, we multiplied this this equation by 1/2, the whole thing. So now the power of this one becomes 1/2. So this K is that one to the 1/2 power. Right? That gives us 2 coppers. We have a 1/2 an oxygen here and a 1/2 an oxygen there, so they would cancel. But we need oxygen on this side, don't we? If we flip that equation around, that puts a 1/2 oxygen over here, plus a 1/2 oxygen gives us 1 oxygen. So if we invert the equation and say copper 2 oxide plus 1/2 oxygen gas yields 2 CuO solid. Okay, we just inverted the equation, right? So that makes this one 1/K2 for that equation, right? We just flip the equation, invert the K. So let's see if that will add up, right? So we've got 2 coppers here, 2 coppers there. We got a 1/2 here and a 1/2 here, makes 1 there. We've got, now we're using this equation and this equation. So we've got Cu2O here and here, they cancel. And we've got CuO here, 2 of them. These have been used up, that one's canceled. This one's used up, that one's canceled, it leaves that one. So now when we add those 2 equations together, we'll get this one. Let's see. Scooching over, there we go. Kind of off screen. So now what happens? Well, now you multiply this one, which belongs to that equation, times this one. So the new K is equal to K1 to the 1/2 times 1 over K2, which is equal to K to the 1/2 over K2. That's our new K value right there. For this combined reaction based upon these two. Okay. Okay, that's what I wanted to show you. What do you do with K's when you add equations together? And we're finished a little early, unless you have some questions. We'll go over this review document next Monday. Right? It's not a big one, but the problems do take some thought. Let's see, we've got, let's see how many there are there. 38. There are 38 problems in here. And we won't have time to do all of them next week, but I will pick out a few that I think are pivotal, that is, that really bring out the most useful salient points of what we've discussed today, and hopefully prepare you for the exams. But then you'll have the spring break to work out any kinks, and I'll be available on spring break. Office hours might be a little iffy, but if you send me an email, then I'll certainly connect with you on Zoom if you have a specific problem. Okay, any questions while I erase the board? And I'll be back at 12 noon for the usual lab tutorial if you need it.